we've discussed indeed this kind of resistance to change, and now this leads us to the work that we need to do in order to install a certain current in our loop. Okay, and here I'll just flash these because again the equations are less physically important than the result that we'll get to. The calculation here computes the amount of work that you need to do in order to install a certain current in a certain loop. Okay, and you remember the work that you need to do, it's really like voltage times current. Power is VI, and now the voltage that we have here is really our EMF, and our electromotive force is given itself by the self-inductance of the loop times the time rate of change of the current going through it. So we have an equation for the work per unit time done on the loop as I am changing the current, I of t, right? And now, if I imagine the simple situation where I start from a loop with no current at t is equal to 0, and I'm just integrating up to a point where I have a certain current, I at t, then I just need to integrate this, which is like a straightforward integral here. The energy that I've poured into the system in order to run current I is 1/2 times L times I squared, where L is the self-inductance of the loop. Okay, so that's the amount of work you need to do to bring up this current. Okay. Now, here there is a derivation. Once again, it's a technical derivation, but it starts from the idea of viewing a generic situation with currents flowing around in space as just a generalization of single loops with current like this. So now instead of having a single loop, what I'm going to have is a volume current moving around. Okay, and this energy that I've just had, this 1/2 L I squared, I can write in terms of a volume integral of current density by just observing that I can write L times I as just the integral of the vector potential dotted into the current. That's really just using the definition of what the flux is. The flux is just the integral of the magnetic field over the surface like this. I write the magnetic field as the curl of the vector potential. I use Stokes' theorem, so it just becomes the integral of the vector potential on the outskirts of the surface, on the loop defining it, just a mathematical identity. And now this one here, I can readily generalize to volume currents for doing this. Maybe what I'll do is I'll leave you to look at that derivation here. Once again, it's just a question of plugging in equations that we know, plugging in Ampere's law, using an identity for the divergence of a product of vector fields, and then reorganizing terms. Okay, so the derivation itself carries no physical meaning. However, the result of this derivation is something that you have to be comfortable with. What this derivation tells you is that if you have a configuration in which you have installed these magnetic fields by increasing your currents in one way or another, then the amount of work that you poured into your system in order to install this magnetic field is just the volume integral of the square of your magnetic field. Okay, so I'll let you go through the derivation and become comfortable with it. Okay, so that's the statement. And you might remember that in the case of the electrostatic field, we had kind of relatively similar. In the case of the electrostatic field, we had a similar expression for the energy, which was so if this was the electrostatic component, this was epsilon 0 over 2, the integral over our volume of E squared. Okay, so you see there's a parallel here. The square of your fields is essentially the energy density per unit volume that your electromagnetic fields are carrying. Okay, so we'll get back to that later when we discuss electromagnetic waves and stuff like that. So for now, this is just the magnetic equivalent of that. And there's also a simple example there that's also in the notes that I just throw there. You've got a coaxial cable with current going inside and then back current going on the outside. You've got non-zero magnetic field inside that thing, and how much energy is contained in that thing per unit length. Well, you can just compute it by performing this particular integral. Okay, so again, I'll let you have a look at this.